Well, hello, honors. This is our new video, Chapter 4, Part 1. What we need to start talking about is what actually causes acceleration. What actually causes acceleration? Well, as it turns out, this is going to lead us into talking about Newton's first two laws of motion. So we need to first start talking about, we will ultimately start talking rather about Newton's first two laws of motion. The second law of motion ultimately is going to be that the net force equals mass times acceleration. The ultimate goal here is Newton's second law. We'll talk about the first law in a second. This is his second law. This is the end game. Net force equals mass times acceleration. This part right here, this silly little symbol, that is the Greek letter sigma, and it's mathematical. It stands for summation. So this law says the summation of all of the forces, the net force, equals mass times acceleration. So if multiple things are pushing on an object, let's say you and your friend are both pushing on an object. So here's some object, you're pushing on it that way, your friend's pushing on it that way, and let's just say your little sister's trying to stop you, silly little girl. Well, the net force, all of that would be that vector plus that vector plus that vector. Okay, so that's all net force means. It just means all of the forces. Okay, mass, well, that's just going to be the mass of this object. So this object's going to have some mass. And the acceleration, well, overall, this is being pushed that way by some net force. So overall, it's going to accelerate that way. And that's ultimately what we're going to start talking about. So before I show you a little video clip, let's just go back and review some notes. Force has the units of a mass and an acceleration. Mass has the units of kilograms. Acceleration is meters per second squared. So force has the units of kilograms times meters per second squared. We're going to give that the special name, the Newton, and we'll just use capital N for it. So force is going to be in the units of newtons. A Newton is going to be a kilogram meter per second squared. A mass times an acceleration. Okay, let's go look at an example of some force causing an acceleration, and then we'll move on to the next topic. So, force causing acceleration. If you look here, you will see a video of a cup, and that cup is just sitting there. Its velocity is currently 0. Once I apply a force, the cup's velocity changes. It actually has some velocity. Who knows what that velocity is, but it was 0. Now it's not 0. I have literally changed the velocity of that cup. Well, if I changed the velocity of that cup, that means the cup had an acceleration. Now, to get the number for the acceleration, we just have to remember that it took some amount of time. When I was sliding that cup over, it took some amount of time, and its velocity changed, which means the act of me pushing on that cup caused an acceleration. So that's good. Force causes acceleration. Okay, so let's go to Newton's laws, and then I want to finish with something called free body diagram. So Newton's laws of motion. We're only going to do the first two. So Newton's first law. Newton's first law states that an object at rest wants to stay at rest, while an object in motion wants to stay in motion at constant velocity. I'll say that again. An object at rest wants to stay at rest. An object in motion wants to stay in motion at constant velocity. In other words, Newton's first law is saying that things do not want to accelerate. Things don't want to accelerate. Newton's second law states that if you want something to accelerate, remember it doesn't want to, if you want something to accelerate, you have to force it. I have to force something to accelerate. That is Newton's second law. Okay? And you just saw that in the video. All right, so We're going to be dealing with problems that involve multiple forces acting on an object, and those forces are vectors, and those vectors just get added together. For now, we're doing one-dimensional problems, so our forces will be one-dimensional. So our forces could either be in the positive direction, sometimes our forces could be in the negative direction. Either way, you add them all up and you get some total force, and that equals ma. Okay? So, how are we going to deal with drawing this stuff? Well, we're going to institute something called the free body diagram. The free body diagram. Well, a free body diagram. Well, that's just a diagram of all the forces acting on some object. So, if I have some object of interest, let's just say, let me back up a second. Let's just say my object of interest is going to be some box, and I'm going to push it across the table or across the floor. Okay, well, then my free body diagram would be a dot representing the box, an arrow representing the force, and some statement about the acceleration. Well, I don't know what the acceleration is going to be, but I do know it's going to be that way. That gives me my free body diagram. Let's look at some examples. Example 1. So this is going to page 89 in your textbook. Practice problem 1. A flower pot falls freely from a windowsill. Ignore any forces of air resistance. All right, so a flower pot falls freely from a window. So a dot represents the object of interest, and it's falling from the window, so the only force acting on it will be the force of gravity. It's going to accelerate, and if the only force acting on it's gravity, we know the acceleration is negative 9.8 meters per second squared. So that gives me the free body diagram. Let's see what else we got. Number 2. A skydiver falls downward through the air at constant velocity. The air exerts an upward force on the person. Okay, so this time we've got a skydiver. Gravity's pulling them downward. The air is pushing upwards on them, so this time we're including air resistance. And it said the acceleration was constant, didn't it? And the acceleration is constant. The velocity is constant, so... Wait, hold on. Velocity is constant. Okay, so if the velocity is constant, that means the acceleration is 0. So there is a free body diagram for that one. I've got the two forces, the object of interest, and a statement about the acceleration. Okay, free body diagrams. Alrighty. I think that covers just about everything we need to talk about here. So I'm going to end the video right there and probably work a couple problems up in front of you at the whiteboard. We'll see you later.